So today I want to do a technical deep dive into how we operate Spinnaker in production at Netflix, and specifically dig into the features that we've added to the system that we're leveraging that are enabling us to run at the scale that we're running at. So we have basically constant API traffic against our Spinnaker instance that is driven by external systems and automation at kind of all hours of the day, which peaks up during sort of business hours. Additionally, we have users that get on the system sort of during working hours, and sort of all told, we peak somewhere over 100 requests per second during the day. Our deployment footprint for Spinnaker at Netflix is we have a single shared Spinnaker that all the users use. Each service is deployed independently, largely because we're developing and iterating on them. But we do have also dedicated clusters for each microservice. This lets us scale them up, changing instance types to give more compute resources, as well as scaling them out to add more nodes. But eventually, no matter how much compute or nodes we give something, we tend to run into bottlenecks. So we can scale up and scale out our services, but over the course of our sort of history of our deployment of Spinnaker, we've run into a number of bottlenecks. In Gate, our API service, we've had poorly tuned Hystrix pools that we've managed to saturate, kind of preventing any requests from getting downstream. In Orca, our orchestration engine, for a long time we had stateful deploys where each deploy was stuck on a particular instance, and we could overwhelm an instance by landing too many deploys on it. Additionally, the persistence that backed our Orca instance was based in redis and not great for the access patterns that service needed. And then clouddriver, which is our cloud integration layer, does a lot of work aggregating and sort of indexing the state of the cloud for all the different cloud providers and accounts that are configured, as well as serving that aggregated model for its API. So as we've been operating Spinnaker, we've managed to unclog a number of these bottlenecks. Gate was relatively easy, tuning and partitioning Hystrix a little bit better. Orca, we undertook some very significant efforts, re-architecting it into a distributed work queue where an orchestration in progress essentially just naturally propagates around all the nodes that are available and is no longer stateful. And we rewrote its persistence backend in SQL recently. I actually don't know if that's merged into open source or not, but that's been a big win for us. Not only from the access patterns that are better for that specific data set with SQL, but also the ability to move it onto a hosted SQL solution. In our case, we're using Aurora on AWS, which gives us a good story around replication as well. clouddriver, not so much, so that'll be the focus of the rest of this talk, mostly. So clouddriver is the service that goes out and crawls the cloud provider APIs, pulls all that data in, aggregates it, serves up API requests. So it's both very read-heavy and very write-heavy. When we initially started out, we first implemented that in memory. It was great, but that doesn't scale past one node because we can't build a sane system where each node has a different view of the world. There was some guy that thought it would be a good idea to put that stuff in Redis, because then we could scale the caching, It would all index somewhere centrally. We could scale the API reads. They would all read from the central spot. So my name's Cameron Fieber. I'm a senior software engineer on the delivery engineering team at Netflix. If you've run into scaling problems with clouddriver, it's probably largely my fault. So sorry about that. But hopefully today we're going to talk about some of the features that exist and the tools that we've built and how we're using them to kind of get past the scaling bottlenecks that exist in clouddriver. And maybe while I'm in the apology mode here, it's also, I guess, worth pointing out that hopefully at some point in the future, all of this talk becomes meaningless because we're very actively focused on addressing these performance problems in better ways than just figuring out how to throw more hardware at it and sort of get past the scaling bottlenecks. So these are, I would say, are very tactical solutions that we've come up with to kind of keep the ship afloat, to put sand on the tire fire as we're actively working to make it better. So we're going to talk about scaling clouddriver, which will lead into some stuff around how we manage redis. Then we're going to talk about scaling clouddriver even more, now that we can manage redises. We'll talk about some of the metrics and monitoring that we use to figure out that we're in a good place or not. A little bit about how we do maintenance, since we're now taking on managing stateful services, and then Q&A time. So we'll start with kind of the basic kind of first step you could take scaling out clouddriver. So in the initial state of the system, you've kind of got deck, your UI where the users are coming in. You've got API users, they're all funneling through Gate. And if Gate needs some information to serve just a read API request, it'll ask clouddriver for that. If the user asks Spinnaker to do something, that flows over to Orca. Orca kicks off that work. As that work's progressing, it's doing a lot of checking the state of the cloud to see, have I got where I'm trying to get to? So the wait for up instances task, which you may be familiar with if you've been sitting there trying to watch your pot boil or your pipeline complete. So all of that is read traffic against clouddriver. So the first pass we can take at sharding out the system, we've kind of obviously identified we've got two different sort of usage patterns, and we've got a system that naturally lends itself to sharding to support those. So we've got write-heavy traffic from our caching instances, and we've got all the read requests that we need to serve the API requests and the state of orchestrations as they're proceeding. So the first thing we can do is introduce some replication. So what we do is we add a read replica, and we stand up another clouddriver cluster, and we call that one our read-only cluster. And because Gate is never actually making changes to the state of the cloud, it can always talk to the read-only cluster. Orca will kick off work that modifies the state of the cloud, but then watch for completion of that work. So Orca can initiate a request to the main clouddriver instance and then do all its read traffic against the read-only replica. So in order to make that partition, we added a read replica. We stood up a dedicated clouddriver read-only cluster pointing at that read replica. And that cluster has its own ELB. It has a dedicated host name. And on that cluster, we disable caching. So there's a feature flag in the clouddriver YAML file, caching write enabled, and we set that to false. And that stops running caching agents against the replica. Gate points all its API traffic against our new host name for read-only. And Orca has a feature where you can say, here's a URL for a read-only clouddriver. So we set that configuration. So a clouddriver read-only URL, and Orca will start watching the replica as it tries to achieve its state of the world. So that's a good incremental step. And kind of another step along the same lines is partitioning out the actual execution of caching. The way the caching works is it's crawling all the different collections in each underlying cloud provider for each account, for each region, and you start multiplying all those together, and you have hundreds plus of caching agents that need to run and be scheduled. As those pull data, they can pull large data sets into memory, process that data, and that can become very sort of memory and compute intensive. So there's a couple reasons to partition that off. One is that you can have a little better control over instance sizing so that you don't, say, blow up memory as those caching agents are running, as well as the sort of the CPU load that executing that caching can actually introduce not so great latencies just in serving API requests off the same node. So this one is fairly straightforward. We add another cluster. So now we have a clouddriver API cluster. This one's read-write. This is where operations are going to kick off from. We have a clouddriver cluster that just does caching. And then we still have our read-only replica that we added because it was a good idea. So now in this model, or at least the way we've approached it, is we added a clouddriver API, and that one actually keeps the hostname and the ELB from our original configuration. In our clouddriver caching cluster, nobody's actually making API calls to it. It just sits there and runs these caching processes. One thing to note is there is some configuration in clouddriver where you can actually tune the number of concurrent caching agents that'll run on a node. And this is really handy for a couple reasons. One, if you're just trying to do local development and you run clouddriver, previously that would like spin up all the fans on your CPU. It would try to mine us a Bitcoin, but it wouldn't succeed. But then it would try and run all the caching agents. With this configuration, you can tune that way back and not actually melt your desk with your laptop. But also for your caching cluster, you can sort of control the number of concurrent executions and guard against loading too many gigantic data sets on one node and crapping it out, blowing up memory or whatnot. So one of the things we did in order to shard this is we added Redis replicas. And it turns out for us that we ended up managing Redis ourselves. And maybe the first question is, why not ElastiCache? Because maintaining stateful services is hard, and it sucks, and it's great if someone else can do it. We started down the path of using ElastiCache initially. We ran into some unpredictable behavior during the maintenance windows. We ran into, and this probably is also related to what was causing us to trigger failover, because this was kind of early in the days of us understanding the performance characteristics, but we found that running an ElastiCache cluster, we would just end up in a state where it would very surprisingly trigger failovers. And then part of that is we didn't have great insight into it because there was just that disconnect between how the ElastiCache publishes metrics and how we like to consume them. So for our Redis infrastructure, we essentially have our own AMI with Redis on it, and we pre-allocate a bunch of Elastic Network interfaces. So each of those corresponding to a Redis instance. We stick an EC2 tag on those that says this is an ENI for this cluster. And we put host names on the IP addresses associated with those ENIs. So those are private IPs in our VPC space, but they're fixed, and we can use DNS naming to address these things. So in our convention, we would have a main cluster as a master. We would have a replica cluster for all the replicas. And then our AMI is aware of that naming convention. And essentially what we've done is we've got a team that manages a base image that kind of all Netflix software runs on. We have a vanilla redis built on there. But this gives us insight via metrics publishing. We also built a pretty simple sidecar app that just monitors Redis by issuing the info command and exports those metrics out through Spectator so that they end up aggregated in the same way as all the other Spinnaker components do. We get an health indicator through Eureka, which we use, as long as the Redis instance is responding to ping. So on startup, this instance will look out for a network interface with a tag that matches the cluster it's deployed in. It'll grab it and attach it. If its cluster name ends with replica, it'll issue the slave of command and connect to the master, and it's good to go. It's all kind of hands off. We just launch one of these. So now that launching Redis is easy, and we have a hammer, everything looks like adding a replica problem. And we're going to talk about how we do that even more. So with our initial partition of a read replica and a master, we're in an all right spot, but we're still in a spot where all of the read traffic is shared to one replica, and one sort of bad actor or really busy deployment or something can impact all of the users of the system. So one of the first user groups that we wanted to address and not impact as much as possible is people that are actually in the UI trying to look at the state of their instances or take action. So for us, if there is an incident and people get involved, very often the first thing they want to do is go in and maybe scale up a server group. Maybe they want to do the automated rollback. But essentially, we don't want some other system that happens to be running a big deployment job to impact the UI in such a way where those people can't take those actions. So one of our heavy API users crushes our replica. We get slow API responses or even timeouts. We get a slower unresponsive UI, and then we get angry users in our Spinnaker Slack channel saying, why is Spinnaker down? So we add another replica, because that's what we do. And we added a feature where deck always adds a header that says X rate limit app is deck. And Gate is able to use that header to do dynamic routing. So we stand up our replica, we stand up our clouddriver cluster pointing at that replica. Excuse me. And then we add some configuration in Gate that tells it to route all this traffic to that replica. So that's fairly straightforward. In Gate, you can add some configuration for dynamic endpoints. So services.clouddriver.config.dynamic endpoints. And so anything with that X rate limit app that matches deck will go to this clouddriver read-only deck replica. And now we've partitioned UI read traffic away from our main replica. So the last sort of thing we're going to do is we want to isolate the big users of the system. We have a number of systems that are constantly running automation that may kick off a very large number of concurrent orchestrations. We've got some services that are deployed that have upwards of 1,500 clusters within their application. So those systems or those tools, when they want to kick off work, can often put a large amount of load on Spinnaker, and particularly if they're kicking off a bunch of concurrent orchestration jobs, can saturate our Redis instance. So we want to solve that problem, but we also don't necessarily want to inflict the solution of that problem on our users. So we kind of constrained ourselves to solve that behind our API layer. We don't want to give out, hey, you get this endpoint and you get this endpoint, or you get this stack and you get this stack. We don't, we don't want to For better or worse, we don't build and maintain a smart client for our API. So our API is just the REST API. So we don't have the ability to sort of push out dynamic endpoint decisions to users of that API. And even if we did, we'd have to maintain it in a number of different languages. So essentially, we want everyone coming into our one, API.spinnaker hostname, and we'll solve it behind that. So now what we can do is add more replicas, because that's what we do. So here we can add any number of replicas that are dedicated to orca traffic. And each of those is set up the standard way. They've got a cluster, they've got a host name and ELB. And we use what's called a service selector in Orca in order to figure out which one of those clusters to land on. So again, we still have the issue of we want consistent reads for a particular user. So as we add all these replicas, they're all in sort of a different state of replication. We don't ever want some particular use case to bounce between different replicas, because you might end up in a state where I read something and I see a server group's there, and then I read and I land on a different replica, and that one's not caught up to the point where that server group is created, so I don't see it, and then my automation gets confused because I saw it and I don't see it. So now what do? Has it got created yet? Did it just get deleted? Confusion ensues. So we want consistent routing to all these replicas, and that's what the service selectors give us. So essentially, we get rule-based routing to all these different clouddriver endpoints that we're standing up in Orca. And we have a list of these clouddriver endpoints. Each one has a URL. They're prioritized because it's very possible to configure these service selectors where it would match. A number of service selectors might match a particular request, so priority lets you control which one wins. We have a few options out of the box for doing this selection. So we can select on the execution type. So is this a pipeline or an orchestration? Really the difference between the two is an orchestration is something that a user in the UI goes in and clicks, like resize or roll back or whatever, whereas a pipeline is an execution through the pipeline configuration. We can select by the authenticated user. So if we know there's some automation like Chaos Monkey that comes in and constantly is issuing termination commands, we could route that all to a particular replica. We have an origin service selector, and that's where we're leveraging that header from deck that flows through the system as an origin. So we can shard by that origin and again ensure that not only are all the reads from the UI on some dedicated infrastructure, but also all the actions that somebody's trying to take. And again, we've got one to shard just on the application that's being operated on. So as a quick example, we stood up 3 replicas here. We've got one that's selecting on the applications. We've got a big app 1, and we've got all of our Titus infrastructure. And we're going to route that to this Orca 1 replica. And we've got another selector. We want all our UI operations to route to a dedicated shard. And then finally, we have just a default. So with no configuration, that becomes the fallback for everything else. So that's kind of the extent of the options that exist for partitioning the traffic in clouddriver. You'll notice it was a lot of partitioning the read traffic. We don't currently have a good story for partitioning the write traffic. So if we got to the state of overwhelming the Redis master, the best we can kind of do is tune back the number of concurrent agent executions to make sure that we don't overwhelm it, and maybe deploy it on an X1 or something like that, and hope that works. So I want to talk a little bit about how we're monitoring to determine that the system's in a happy state. And ideally, it's not our users in our Spinnaker channel in Slack, but sometimes, often it is. It's just unfortunate. So we've heavily instrumented all of Spinnaker with metrics, and they're all published out. If you're using the Spinnaker monitoring component, all these metrics should be available. But here's a few key ones that we use that give us a good indicator of sort of the health of this Redis infrastructure specifically. There's a metric, controller invocations, and that exists on all the services. This gives you timings of every API request. For us, we can use this to alert on our read replica APIs. If they get really congested, then those timings will shoot up. And we have sort of identified some good thresholds there that for us are worthy of alerting on. We have a counter, so all of the caching agents that run will just increment a counter, and they'll tag that counter with the success or failure count. So we can alert on caching agents failing to complete successfully. This can be an indicator that the Redis master is overloaded. This can also be an indicator that the underlying cloud platform is serving up some errors. Either way, it's usually a good thing to be aware of. But probably one of the most interesting metrics, and this one comes from our little sidecar, but it's essentially the, if you did a Redis CLI info replication, one of the items in there is is called the slave delta, and that's the number of bytes that a particular slave is offset from the Redis master that it's connected to. Excuse me. So in kind of the steady state normal case, these offsets are relatively low in the sort of order of megabytes at most. But what we'll see is a couple of different examples of when things go sort of sideways. So one example is we'll see one replica and it'll just start getting lagged. And it'll get into this situation where it's essentially unrecoverably lagged because it's got so much data to ingest from the replication stream that sort of any ongoing API request traffic against that puts too much load on it for it to ever get caught up. The other thing that we'll see, so that's like a single replica kind of going bad. The other thing that we'll see is all of the replicas start to go bad at the same time. And that's generally an indicator that there's too much churn from the master. We haven't really seen that in a long time, except for very recently, our sort of proxy layer between the AWS API and our caching infrastructure got into a bad state where it was flopping between a really old view of the world and a really current view of the world. And we were constantly evicting everything out of the cache and recaching it. And that tipped us over and ruined a weekend for some people. So kind of the next thing I want to talk about is maintaining this, this infrastructure. So we've added all these instances. They're all stateful instances. We need a way to be able to apply security patches. We need a way to be able to update the version of Redis. We don't really have a deployment window where we can take things offline to do this kind of stuff. And we really don't want to do any sort of mutable infrastructure types of things. So we still want to stick with an immutable infrastructure model where we're pushing out these AMIs. So I know we'll add more Redises. So essentially what we do is we have our current stack of all these replicas and all these clouddriver clusters that are reading from these replicas. And we just basically rubber stamp that into another batch. So what we stick in our naming convention for our clusters is we call one of them A and we call one of them B. And in our steady state, we're operating against one of the two of those. And if we need to make infrastructure changes to push out a new Redis version or whatnot, then we run a deployment where we essentially move everything onto a new set of instances. And really, the one thing that we need to enable there to make that like seamless-ish is as clouddriver is running tasks, it's writing an update into the Redis database tracking the state of that task execution. And so when we end up on a new Redis instance, we support reading, and I probably should have put this configuration property in here, I apologize. We support reading from the previous Redis. So there's actually a configuration property, redis.previous connection. And so if we deploy to if we're running on dash A, we deploy to dash B, it knows to connect to the dash A Redis if it ever gets a cache miss looking up task information. So this is what gives us the sort of ability to deploy a whole new set of Redises. And this is actually what we leverage if we get to the point of replicas going sideways and never going to get caught up again, is we just deploy onto a fresh Redis instance. And I'll sort of show you what that looks like. We call that the flippy-floppy-flush. So essentially in our steady state, we're just deploying clouddriver updates by a simple red-black deployment pipeline. But in the Redis maintenance case or the emergency, we flip onto the other Redis stack and we flush or recreate that so it essentially starts empty from a kind of happy path. There's a little bit of a scripting call in there just that we use. We make an API call to our Spinnaker instance or our Spinnaker API that says what is the current stack. Are we currently on A or are we currently on B? We just do that by looking at all of the clusters in clouddriver, and if we see, well, there's a bunch of dash A's and no dash B's, then we know we're currently running on A, we're flipping onto B. So we just export out of that scripting call some parameters, and we feed that into the rest of this pipeline. So we have one deployment pipeline for clouddriver, and that can either do our happy path, regular software push, or this full-on flip. So our happy case is fairly straightforward. We look up an image, we deploy, we've kind of partitioned our deploy into caching agents first, and then the rest of our API clusters. That's less important for this happy path deployment, but it lets us for the flippy-floppy-flush. It lets us push these caching agents, and then we have a wait stage in there. It's parameterized. So in the case of this rebuilding the world mode, we just dynamically stick a wait in there and say, okay, well, we're going to run this for 5 minutes, let all the caching agents run and populate data, and then we'll proceed with the deployment to the API nodes. So all our API nodes are, for both our A and our B, are behind the same load balancers. So we kind of violate our don't give people inconsistent reads, but we try and be in that state for as short a time as possible. So as we fail over onto the other one, then our pipeline proceeds. It uses a sort of an expression or a conditional check to figure out, okay, did I do this failover deploy? Now I'm going to go and tear down all the old infrastructure that was associated with the other stack.